This is Math 251, and we're looking at section 12.7. We'll talk first about tangent planes, and then we'll end with linear approximations and differentials. So tangent planes. If we start thinking about our surface, z equals f of x and y, right? Graph some sort of a surface here. Of course, if you think about a point P, there would be infinitely many tangent lines at that point, right? There'd be all kinds of different tangent lines at that point. However, all of those lines lie in a single plane that is the tangent plane. And our goal right now is going to be to find out, or to find a way to find the equation of that tangent plane. Right. There's a little bit better picture. Well, I shouldn't say better. I don't know if you'll think it's better or worse, but a more three-dimensional one down here. You can see this is kind of like the point P right here, the point of tangency. And the blue is the initial curved surface, and then that kind of orangish is the tangent plane that's just touching the surface at that point. All right, to find the equation of the tangent plane, what do we need to know? Well, we need to know the same two things that we need to know to find the equation of any plane. We need a point, and typically that's no problem because it almost has to be given to us. It's the point P, the point of tangency. And then secondly, we need a normal vector. So I need to find this vector n that's perpendicular or normal to that plane at the point P. Once I have those two items, then of course I can just go to my usual equation of a plane. Remember this one? We haven't used it for just a little while, but we used it back at the beginning of the chapter. And as soon as we have our point P, that gives us the x naught, y naught, and z naught, and then our normal vector that gives us the a, the b, and the c. So right now we're going to concentrate on how do we find that normal vector, because at the moment that seems to be the only thing standing between me and knowing how to find this equation of this tangent plane. In order to find the normal vector, I need to go back to something that we kind of ended with in the last section. You might even recognize that picture because it's one that we actually drew something very similar with Maple in the last section. What we're going to do is we're going to extend a property of the gradient that we were just talking about. Remember how we said that if we take a surface like this and we slice it through to make level curves, then the gradient vectors are always perpendicular to the level curves, right? This would be the gradient of f at the point 0, 2. And it's perpendicular to the curve at the point 0, 2. And so on. I need to three-dimensionalize that concept. I would now like to think about a function of three variables. W equals f of x, y, and z. Now, remember that we can't actually visualize a graph of that function, because to graph it, we would need a fourth dimension. The x, y, and z would be the inputs, and we'd need a fourth variable, w, to plot the output. So we really can't visualize a graph of that function. However, if you can kind of in some corner of your mind accept that if there were a graph, we could slice it through, just like we did with the level curves before, but instead of going from a three-dimensional graph to two-dimensional level curves, what we would be doing here is we would be going from a four-dimensional graph to three-dimensional level surfaces. So we now have level surfaces of our graph. We can't visualize the graph itself, but we can visualize the level surfaces. Just like with level curves, the way we find level surfaces is by setting our function equal to some constant. So we take w and set it equal to a constant. And then we can graph f of x, y, and z equals a constant. That's only got 3 variables, so 3 dimensions. Since in the 2-dimensional case our gradient vectors were perpendicular to the level curves, it seems logical to assume that in this case our 3-dimensional level surfaces will have as their normal vectors the gradient vector as well. So that's what we're going to do. We're going to get the normal vector that we need by simply taking the gradient vector of the level surface. The thing that you really want to concentrate on here, what's going to make this go right or wrong for you, is to always be sure that you are using w equal to a constant. So if you are given an initial form that's not equal to a constant, doesn't have to be 0 necessarily, just a constant. But if you're given any form that's not equal to a constant, you need to make sure that you get your equation to equal a constant before you take the gradient. And that will give you your normal vector. All right, let's try a couple of examples. By the way, that whole process is written out for you at the top of page 44. It's there to use as you need it. I'm going to jump right in, though, to the example. So here we are in example 1. I'd like to find the equation of the tangent plane to this surface, z equals the natural log of 1 plus xy, at the point where xy equals 1, 2. The first thing I need to do, as we just mentioned, is to make sure that my equation is equal to a constant. So I'm going to take the equation that I was given, and I'm just going to rewrite it. I'm going to subtract that natural log to get that to equal 0. Okay. Because I now have a constant on this side, it's okay for me to consider this my function w. Notice that is a function of 3 variables, and so my gradient vector will be 3-dimensional, just like I'm expecting. So, our normal vector, the gradient of w, would be w with respect to x, w with respect to y, and w with respect to z. That's going to be a negative let's see, my derivative for my natural log would be 1 over the 1 plus xy. And then chain rule on that, the derivative of the inner function would just be y. For the derivative with respect to y, basically the same idea. Start with negative and then 1 over 1 plus xy. But my chain rule on this one would be x. And then the derivative with respect to z, nice and simple, it's just 1. Now our point is when x is equal to 1 and y is equal to 2, right? That was the point I was given. So let me just go ahead and plug that in, and then I'll have my normal vector. So now I have negative, y will end up on the top, so that's a 2. And on the bottom I'll have 1 plus, 1 times 2 is 2. Negative, x is 1, and again, 1 plus 2 on the bottom. So my normal vector ends up being negative 2/3, negative 1/3, 1. All right, nothing wrong with using that as a normal vector, but the normal vector doesn't have to be of any particular size. It can be any length. And just so that I don't have to mess with those fractions constantly, if I want to, I could just go ahead and multiply through by 3. I won't change the direction of the vector, it'll just be longer. It's still normal to my surface, and so I can still use it, and I'm not stuck with those fractions. So I'm going to go ahead and use this as my normal vector. All right, a point, P. I was specifically given x and y, right, as 1 and 2, but I do need a z value to go with that. This is a three-dimensional normal, so I need a three-dimensional point as well. So I would have z equals, remember it was the natural log, I'm just going back to the beginning, natural log of 1 plus xy. So in this case, that would be the natural log of 1 plus 1 times 2, or the natural log of 3. For now, I'll just leave that there. I may change that to a decimal a little later on, but we'll keep it for now. All right, so my point is actually 1, 2, ln 3. So it gives me an a, a b, and a c, an x naught, a y naught, and a z naught. And I'm just ready to put the pieces together to find the equation of my tangent plane. So -2 times x minus 1, -1 times y minus 2, and +3 times z minus ln 3 equals 0. Little bit of algebra here. And our usual standard form, we leave all the variables on one side, and I'm going to move the constants to the other, because that would be a -4 and a +3 ln 3. And again, if you want to, you could always change that right-hand side and get a decimal approximation. I'm just going to leave it like that. Right? So that's the typical way of finding the equation of a tangent plane. Make sure your original equation is equal to a constant. That's your W. And then you'll always get your normal vector by taking the gradient of W. Gradient will be perpendicular to the surface. Let's do one more example. So this time I want the plane tangent to the graph of xy squared equals 10 over z cubed at the point 5 square root 2, 1. So I don't have to do any work to get the point this time. They gave me the whole thing. There's x naught, y naught, z naught right there. I do need the normal vector though. So I've got my original equation. And again, I need to get that equation in the form something equals a constant before I can call it W. Now I could subtract if I want to, but actually if I multiply by the z cubed, I think I'll have a nicer equation. So I'm going to choose to do it that way this time. And I now have an equation equal to a constant, meaning I can call this W. So my normal vector will be the gradient of W, which in this case with respect to x, I'd get y squared z cubed, taking the derivative with respect to y, 2xy, z cubed, and finally with respect to z, 3x y squared z squared. I'm going to go ahead and plug in my point, which was 5 square root 2, 1. And let's see, that's going to give me square root of 2 squared, 1 cubed, 2 times 5, square root 2 times 1 cubed, and 3 times 5, square root 2 squared, 1 squared, is 2. 10 square root 2, and 15 times 2 would be 30. Once again, there's nothing really wrong with that, although oftentimes if we can make the numbers smaller, it's nice. So in this particular case, I might just take a moment and divide by 2. Again, multiplying your normal vector by multiplying or dividing it by anything only changes its magnitude. It doesn't change its direction, so I'm going to choose this time to go with 1, 5 square root 2, and 15. All right, there's my A, B, and C. So I've got everything I need to find the equation of my plane. Let's see, I would have 1 times x minus 5 plus 5 square root 2 times y minus the square root of 2 plus 15 times z minus 1 equals 0. And again, we'll run through a little bit of algebra here. What's that? 5 times 2 is 10. So my variable is x plus 5 square root 2 times y plus 15z, 30. And there would be the equation of my tangent plane. So that's finding equations of tangent planes. Now, the good news about linear approximations, which is our next topic, is that really you already know how to do them. If you think about it, imagine a surface. In this particular case, I happen to be using an ellipse as my surface. And imagine a tangent plane just touching the ellipse at some point of tangency here. If I want an approximation for another point on the ellipse, another z value maybe over here, what we're going to say is this point on the tangent plane is an approximation for the point on the ellipse. And of course, the closer I stay to the point of tangency, the better that approximation is. So these are close to the same near the point of tangency. For my illustration, I didn't draw my points very close to the point of tangency because I wanted you to see what I was talking about. But again, if I stayed really close to that original point, the point here on the green surface and the point on the blue tangent plane would have been very, very close. So what we'll end up doing is using the point on the plane as an approximation for the point on the surface. And that is a linear approximation since planes are linear. All right, so I'm going to use what we already know about finding equations of tangent planes. I'm going to find the equation of the tangent plane and then use it to do the linear approximation. So here we go. I've got a function f of x and y is the square root of x squared plus y squared. And I'd like to find a linear approximation for f of 3.06, comma 4.1. So step 1 is going to be to choose a point of tangency. Now the trick to choosing a point of tangency is to pick something that's pretty close to the point you want, and yet is really easy to substitute into your function. So in this case, it's probably fairly obvious. 3, 4 is real close to this point, and of course it's very easy to plug 3 and 4 into my original function. So in this case, let's choose 3, 4. Step 2, we're just going to find that tangent plane. That's the linear approximation. So in this case, let's see our point. We already have the x and the y values. I can get the z value just by plugging into the original. That would be the square root of 25 or 5. So my point's going to be 3, 4, 5. The normal vector? Well, let's see again. I'm thinking of this as z, and I know I need to get that equal to a constant before I can do a gradient to get my normal vector. So let's just go ahead and do z minus the square root of x squared plus y squared equals 0. Now that it's equal to a constant, it's okay to call this w. And my normal vector is just going to be the gradient of w. Derivative with respect to x, I'll get a negative 1/2 x squared plus y squared to the negative 1/2 times 2x. Very similar for y. Chain rule is just a 2y here. And then the derivative with respect to z is just 1. Let's see, I can let some 2's cancel. And I'm just going to clean that up a little bit. Minus x over the square root of x squared plus y squared. Minus y over the same thing. And 1. So finally, to get my normal vector, I'll plug in my point of tangency, the 3 and the 4. And I'll get negative 3. That's a square root of 25, right? When I plug in 3 and 4, so that's just 5. And then negative 4/5. And then 1. Or if I multiply by 5, just so I don't have to deal with the fractions, I could use negative 3, negative 4, 5. So I've got the ABC for the normal vector, and I've got the x naught, y naught, z naught from the point, and I'm ready to find the equation of the tangent plane. So I would have negative 3 times x minus 3, negative 4 times y minus 4, and positive 5 times z minus 5 equals 0. Run through the algebra. And it looks like I've got negative 3x minus 4y plus 5z, and that's just going to equal 0. All my other constants cancel out. So there's my tangent plane. And then my last step is to actually do the approximation. So I'm going to now say, all right, the real x and y that I wanted to approximate for were x is 3.06 and y was 4.1. So I'm just going to plug those in here. And then I'm going to solve for z. I'm running out of room, so I'm just going to go ahead and do that. What would that be? 9.18 and 16.4 is 25.58. Oops, that's 5z. And so if I divide that by 5, I get 5.116 for my approximation. We can, of course, determine how good that approximation is by actually going back and with a calculator. Of course, it's not difficult to plug these values into the original function. If I took the square root of 3.06 squared plus 4.1 squared, my approximation was really, really good, wasn't it? I got 5.116, and that's actually good all the way out to the, hundred thousandths place is the first place that it would disagree with me. So we got an excellent approximation using this technique. Of course, our point of tangency was very close to the point that I really wanted. All right, last little comment about this. You may be thinking, well, gosh, why did we ever even bother? It was so simple to just plug that into the calculator and get the exact value. And of course, that's true. Linear approximations are largely of historical importance. Without a calculator, finding a square root was kind of a pain in the neck. Whereas, notice here, once the function is just linear, even without a calculator, this would not have been difficult to solve for z. So linear approximation mostly was a technique that was used prior to the advent of all of our computational techniques. We still study it in calculus as sort of a historically interesting technique. All right, we're going to come back for one more idea, differentials, in this section in the next video.